Okay, this is going to be the third video on how to find the volume of a solid using cross-sectional areas. And in this video, we'll use cross-sections in the shape of a semicircle. Now, in the first video, we used exactly the same problem where we found the region and the area of a base. And in the first video, the shape was in the form of squares. Now, in this video, it'll be in the form of semicircles, and the picture that your books will probably give you will look something like this. Now, before you start the problem, let's visually compare what you're solving for this time compared to what we solved for in the first video where we used squares. So, rather than using a semicircle, if you use a semicircle, it looks something like this. But in the first video, just a reminder, we used squares, and those squares would look something like this. So we had a square cross-section, and to remind you of what the solid looked like when you did this, the solid looked like this green object right here. So everything else in the problem was the same, but the cross-sections were in the shape of a square. And if you use a square, then you get something that looks like this. So how does it change if you change the shape from a square to a semicircle? And let's just visually do it on this thing where you can see. So first of all, rather than having a square cross-section, go ahead and insert a semicircular cross-section, and it's going to look something like this. So this is going to be a semicircle, and we'll go ahead and remove this square. So the new cross-section is going to look something like that. Now, that's going to change the shape of the solid from this large green solid. The new solid will look like this. It's going to be a solid that the cross-sections are based on semicircles. So removing the square solid, the new shape looks like this. So it's got a semicircle for a cross-section, and the final solid will look like this. And we'll go ahead and just remove this red axis real quick. Let's take a look at it. So it's going to look like this. And your job in this problem is to use cross-sectional areas to find the volume of this green solid. So let's go ahead and we'll put our axis back on. And sometimes the book gives you an outline of the shape, sometimes it doesn't. So it's possible that your book might actually just look like this. It shows you the base and the solid. Okay, so we're finally ready to start the problem. Now, we're going to use the same series of steps that we used in the first video, and those steps look like this. So I suggested these 6 steps, and if you haven't done it yet, I would definitely watch the first video just to give you an idea of how to use these steps. But it comes down to this. The first 2 steps involve sketching what the problem looks like, and the last 4 steps involve solving the integral to actually find the volume. So let's begin, and we'll run through these things one at a time, just exactly like we did in the first video. So the first sketch says, or first step says, sketch the base of the solid in the XY plane using the boundary conditions. So let's go back to our figure. And again, just like in the previous videos, this is the 3-dimensional sketch that the book gives you. But for a lot of students, this sketch is hard to draw. So my suggestion is come over here and on your homework page or on your test page, just use a working sketch. And the working sketch would look something like this. It's going to be the same thing, except that you're looking at it straight down from the top. And the only advantage this offers, it just makes it a little bit easier to draw. So, the first step says sketch the cross-section in the XY plane, and looking at the boundary conditions up here, that's these black equations. So first of all, let's go ahead and sketch what the base of the solid would look like. So you've got x is equal to y squared. Now that's a parabola that's symmetric about the x-axis. So the first thing we'll do is just go ahead and sketch that parabola. So sketch that on your page. Then the next thing says, right now it's open, so it doesn't have a restricted area. So if you add the restriction that x is equal to 4, well, that's just a straight line that goes perpendicular to the x-axis through x is equal to 4, and it would look like that. Now, that encloses an area, and when you enclose that area, that's going to give you the base of the solid, which is what it looks like this in 3 dimensions. Okay, now the next thing is to actually sketch one section in the shape of the solid that you've been given. So in 3 dimensions, it looks like this, and we'll do something similar to that over here. So let's go back and look at our steps again. We've completed step 1 and sketched the base of the solid in the XY plane. Now the next one says that sketch a single cross-section in the required geometric shape. So we're going to sketch a single semicircle cross-section. And what that would look like, and again, I'm going to go over here to do this. But just like on this one, you begin with a baseline. So let's go ahead and start with the base. So you just come in some distance x, draw a baseline, and from that baseline, you draw the section. Well, we'll do the same thing here. We're going to come in some distance x and just start by drawing a baseline where you've got someplace to start with. So I think I'll start it from here and go down to, say, here. So there's my baseline. Now, I roughly want to draw a semicircle, and it doesn't have to be anything really great, but I'll just draw a semicircle that will look something like rough semicircle that'll look like this. Now you want to give it some thickness because there's going to be a dx involved, so I'll draw another one that looks something like that, just to give my sketch a little bit of thickness. So I'll put it like this. And I come in and shade these a little bit. I'll leave it up to you how much detail you want to put in there, but we'll shade these. And what that is one section of a semicircle. That is what this is right here. Now the thickness of this little thing is going to be dx. That's why you want to put a dx on it when you get around to using your phone. So it's got a volume to it. And what you're going to do is find, first of all, the area of this shape, and then when you multiply it by dx, you'll have the volume of just that little section, or this section right here. Okay, now let's go back to our rules again. So we've got the sketch done, both 1 and 2, and you sketch a single thing. Now the next thing to do is to come up with a general geometric formula for whatever that given shape is. So this is where you want a general formula for the area of a semicircle. So we'll scoot down just a little bit, and let's go ahead and put that right here. So I'll put this is going to be the area of a semicircle. So the area of a semicircle is just the general formula. And what that's going to be would be, now the area of an entire circle is pi r squared, pi times the radius squared. So the area of a semicircle would be 1/2 of that. So 1/2 of pi, and then whatever the radius is, times the radius squared. And what this is the general formula for a semicircle. So let's go back to our steps again, and you've got step 3 done. Now what step 4 says is this: rather than working with the general formula, to be able to evaluate this integral later on, you're going to need the cross-sectional area specifically in terms of the figure that you've got. So this one says, find the area of a single cross-section in terms of x as it applies specifically to your figure. So let's go back and see what that does. Okay, so what this is the general formula, and the radius is going to be this. So this distance from here to here would be the radius. So that's going to be the radius of the circle. Now, in terms of our sketch, it looks like this. You came over a general distance x here, then you went up a general distance y. So the coordinates of this point right here are the point xy. So y is the radius of your circle. So the radius of the circle, the way we've got the sketch drawn, is going to be y. So I need to put this general formula in terms of my sketch, and in terms of my sketch, it's going to be 1/2 pi, and in place of the radius, I'll replace it with y, but it's going to be y squared. So what this is going to be the area, I'll put it this way, the area of the semicircle, but with one important thing, it's going to be in terms of y. So right now, it's a function of y. So let's go back to our rules again. Now, when you evaluate the integral, it's going to be in terms of x, so everything in the integral has to be set up in terms of x. So the next thing you have to do is change the area from an expression in terms of y into an expression in terms of x so that you can put it into this integral. So let's go back and see how to do that. So now right now I've got the area in terms of y is 1/2 pi times y squared. But I've got to get it in terms of x, and the way you get it in terms of x is to go back up here and use the equations that gave you your boundary conditions. So you know that x is equal to y squared, so we'll take advantage of that and come down here, and we'll do the following. I know that x is equal to y squared from the boundary conditions, so take the square root of both sides, and you'll get the square root of x is equal to y. And you can use that over here to change this in terms of x. So what I'll do now is I'll write it as this, as 1/2 pi, and in place of y, put what y is equal to, which is the square root of x. So that's going to be the square root of x squared. Okay, so what that gives you is 1/2 pi, and the square and the square root cancel out, which just leave you with an x. And what this is going to be the area of that semicircle in terms of x. And that's important because to evaluate the integral in terms of x, everything has to be in terms of x. So we'll put a little box around this. So what this is the area of that semicircular section right there. Okay, now let's go back to our steps again. And the next step says this. It says determine the limits of integration, and you can get these right off your sketch. So let's go back and take a look at that. So what happens is dx is here, so we're going to evaluate it along the x-axis. So you're going to evaluate it from this point right here, where x is equal to 0, and you're going to go straight across to this point right here, and that's going to be where x is equal to, and from your boundary conditions you know that x is equal to 4. So those are the limits of integration from 0 to 4. So now it's just a matter of, let's go back to our steps again. The final step is to evaluate the integral to find the volume. So what you've got is the volume is going to be, for a single cross-section, it'll be the cross-sectional area, and dx is the thickness of that cross-section. So when you multiply area times thickness, you'll get volume. And when you integrate it from A to B, you'll get the volume of the entire solid. So let's finally go ahead and evaluate the integral. Okay, and we'll scoot this down just a little bit where we can see what's going on. So now I finally want to do the volume. So the volume is going to be equal to the integral, and I know it goes from 0 to 4, of the area of the cross-section in terms of x, which is 1/2 pi times x. And then the whole thing is dx. And what that is nothing more than this equation right here. So volume is equal to the cross-sectional area times dx. So it's just a matter of putting that in. Now let's go ahead and evaluate that integral. So what this is going to be, now first of all, I can bring the 1/2 pi to the outside, so I'll make that be pi divided by 2 times the integral from 0 to 4 of x dx. So it actually turns into a pretty simple integral. Okay, that's going to be pi divided by 2, and this will become x squared divided by 2 evaluated from 0 to 4. Okay, so that's going to give you pi divided by 2 times, and plug in the 4, so 4 squared divided by 2 minus 0 squared divided by 2, and it looks like that. So this is all going to wind up giving you 16 divided by 4, which would be 4, and the whole thing will turn out to be 4 pi. So what this is, in exact terms, this is the volume of that green solid. Now, if you change that to a decimal, you'd get 12.57. This is going to be the volume of the solid in approximately in a decimal, so 12.57. So let's go back up to our picture now and see what we've actually got. So what the 12.57 is, if you go back and put the solid back on here again, and let's go ahead and remove that red axis again, the volume of this green solid is 4 pi, or 12.57. And again, just to run through the rules one more time, you begin by sketching the base and sketching a single cross-section. Then you found a general geometric formula for the given shape, and then you had to change that general formula into a specific formula in terms of x for your problem. So in our case, we found the general formula right here when you started. So this was the general formula. and then you turned it into a specific formula. Now, initially we had to turn it in terms of y, and then use the boundary conditions to change that in terms of x. So you come up with a specific formula in terms of x for this problem. Then it's just a matter of taking that specific area, which is what this is, putting it inside the integral, evaluate the integral for the answer. And it would look like these final steps right here. The integral from this cross-sectional area in terms of x times the thickness. So, back to sketch one last time. So again, in the first video, it was a square cross-section, and you got a volume using square cross-sections. In this case, it's a semicircular cross-section, and we'll do some additional videos with other shapes in the future here.